Hi, this lecture is a lecture introducing you to a simple connection between the resistance R of a device made out of some material and that material's resistivity and shape. So here are some basic relationships that I'm going to start from. This is our simple model for the relationship between current density and electric field and resistivity. And this right here is a fundamental description of the relationship between the electric field component in some direction called S and the derivative of the potential with respect to small changes in location in that direction S. And there's the associated minus sign. Okay, so yeah, with these two things, I'm going to give you a simple connection between resistivity and shape and resistance R. And so the way it goes is you do the following thing. First, I'm going to drop the sort of vector aspects, right? So I'm just going to talk in terms of scalars. So I'll just drop the vector part. But I know that the current density is going to flow in the direction of the electric field, right? Because you can see that the equivalence is between these vectors, which means these two vectors must have the same direction, right? Okay. And another thing is I'm going to sort of make something of an approximation here. I'm going to say that the reason why we have an electric field in a certain direction, direction S, is because there is a potential difference over a distance S. And so this is an approximation, honestly. Right? But I'm going to make it. So there's the electric field in that direction. I'm just calling it S. But S is actually a difference. It's like a displacement. It's a difference between two places. And those two places have a difference in potential associated with them. And there's, of course, a minus sign. Right? But what I'm going to do is I'm actually going to drop this minus sign. And it's not really part of the approximation. It's simply just because I don't really care about, all I care about right now is I want to just care about, right? I dropped the vector direction, so I'm talking in terms of magnitudes. And over here, I'm going to drop the minus sign and strictly talk in terms of magnitudes. So I have a potential difference. I'll imagine thinking of it as a positive potential difference, right? Some number of volts. And that number of volts is across a distance called S. So at this point, what I'm going to do is just take this E in this S direction, and I'm going to move this volts per distance and put it right there. So now I've got J equals 1 over rho, and then the potential difference divided by the distance in the direction of that electric field. So these are S's for displacement. All right. And now I'm going to remember a third relationship, which I'm also going to make an approximation with. It's that the integral of J dot dA is the current I through some area A. And the approximation I'm going to make is I'm just going to say that the current density, I'm going to make an assumption that the current density is uniform over the area, and it's simply that I is the magnitude of this thing called J times the area A, right? This is an approximation as well. So this magnitude of J, I just call it J, so let me just do J times A. So I've got J, and I've got this stuff here, so I'm just going to multiply by A. So J times A is 1 over rho delta V over S, and then multiply by A. And this, oops, is current, right? Current is J times A, and here's J times A. So now let me rearrange this a little bit, because look at what I have. I have voltage on the left-hand side mixed in with some shape issues, like a distance called S along which the electric field was acting, the area A, which is transverse to the direction in which the electric field was acting. Remember, the electric field and the current density are in the same direction. And I am taking the flux of that current through that area, right? But anyways, I've got voltage, I've got shape issues like the area and a distance. I have material issue here. It's 1 over the resistivity, and it's equal to the current. So the voltage and the current are being related to each other, and 1 over rho A over S is the proportionality between voltage and current. So the way that Ohm's law says this, though, is that Ohm's law says that delta V is equal to I times R. So let me solve for delta V in the expression right here. So if I solve for delta V equals, right? So I'm going to do rho times S up top, and then I'm going to divide by A, right? So rho S and A moved over. It's multiplying the I. So I can identify this thing sitting right here as resistance. Rho is the resistivity, right? It's a question of what material are you using? Are you using silver or gold, copper, steel, right? S is distance along which current flows, right? And A is a cross-sectional area. So here is what this thing is tailor-made for. If you imagine you have, for example, here is a cylinder. The face area is A. Let's say the length of this thing is called L. And we are going to take a couple of pieces of metal. So here's a piece of metal I'm going to tape or embed on one side. And here's a lead. And the other piece of metal is over here. And here's another wire coming off. Now, if I maintain a potential difference, right? So here's let's say that this conductor on the left-hand side of area A is at, say, 10 volts, right? That's the potential, the value of the potential of one conductor. Let's say the value of the potential of this other conductor was negative 10 volts. Then that means that between these two conductors, along the distance L, is a potential difference of 20 volts, right? Because this is 10 above zero and this is 10 below zero, so the difference is 20. And let's further say that this material is characterized by resistivity rho. Then what I can say is the resistance is equal to whatever the area is, their cross-sectional area through which the current gets to flow, right? So that's, oops, that actually goes downstairs, doesn't it? So the resistance has the area below. Here's the area below, resistivity on top, and the distance over which the voltage changes on the top as well. So this will be rho L, right? L there, and then divide by the area A, like that. And I say there's a potential difference of 20 volts. I can calculate the current. So the current is the potential difference, man. So delta V from front to back, right? Divided by the resistance. And delta V in this example is 20 volts. And if I knew, say, the length, let's say the length was 2 centimeters and the area was 1 centimeter squared, for example, right? So this is, it looks like some radius such that pi r squared is 1 centimeter squared. And the resistivity, remember, is in omega times meters. Let's just make up something. How about 5 omega meters, right? So that's the resistivity. So the resistance is equal to 5 omega meters, right? That's resistivity. The length is 2 centimeters. And then I divide by the area, right, is 1 centimeter squared. So if you go through, one of the centimeters cancels, top and bottom. 2 times 5 is 10. Nothing can cancel the ohm. And then I've got meter per centimeter. So remember, a centimeter is 10 to the minus 2. So this is 10 to the positive 2 on the top, right? Because a meter divided by a centimeter is 100. So this multiplies by 100, and this is 1,000 ohms. So let me shortcut to it. So it's a 1 kiloohm. That's the resistance in this case of data. And then the current is, there's a 20 volts of potential difference between these two conductors, where each conductor has a different potential value, right? 10 on the left, negative 10 on the right. So the current is now, I've got 20 volts is the potential difference. The resistance is 1 kiloohm. So it's 20 volts over 10 to the 3 ohms. And the volt per ohm is the amp. And 20 over 10 to the 3 is 2 over 100, or 1 over 50. 1 over 50 amps. Right, so I've got this current. Yeah, so this is a current. The current is going to flow, right, as labeled by I. It's a conventional current, and the conventional current is flowing towards the right from the high potential to the low potential, right? Remember, it's higher on this side than on that side. This is the big value, and this is the little value. And the conventional current goes from high up down to low down, right? So that's the direction from left to right. But if you remember, conventional current labels the way that the positive charges would flow if they were able to. But the truth is negative charges flow in materials because those are the free conduction electrons. So the electrons actually flow leftward, even though we label the conventional current as being towards the right. The conventional current points us down the potential hills from high down to low. Right, so conventional current, in a sense, spills down the hill, down the potential hill. Okay, so yeah, so that's an example. I want to tell you another example too, though. Some problems give you resistors of funny shapes. So here's an example of a funny shape. I've got some radius here, right, of a disc, And then over some length, I have a different radius, radius 2. And we're going to imagine current, or a potential difference. We could say that a conductor on the left-hand side, let's make this piece of metal, we'll hold it at a potential, say, of 6 volts. And this one, we'll say, is at 0 volts. So 6 volts and 0 volts is a potential difference of 6 volts, right? So I've got 6 volts potential difference. But the problem is I don't have one value for the cross-sectional area. So how do you do this problem? The way you do this problem, right, we want to know what current flows, what's the resistance. So these are questions. What's the resistance of this device if we know it's got resistivity rho? If the length of it is called L, right, from front to back, and the radius changes, right? Let's say that's a straight line. So the radius changes sort of constantly with a constant slope from radius 1 up to radius number 2, right? So L is some distance, radius 1 is some other distance, radius 2 is a third distance, right? So it's got a really interesting shape. How do we do this? How do we get the resistance? How do we get the current? Well, if we get the resistance, it's really easy to do the current. The current, if I know the resistance, it's just simply Ohm's law. It's 6 volts divided by whatever the resistance is. But this is the hard problem. The solution to getting the resistance is to imagine our shape cut up into an infinite number, of disks. So this thing right here, we imagine it splitting up. Here's a disk of a bigger radius, a bigger radius, bigger radius, bigger radius, right? All the way through. And the current is going to flow through each of these, where each of these disks has a thickness, dl, and a radius, r, like this. So each disk has an area that's just pi r squared, and the thickness is dl. And so we're going to imagine that each of these disks gives us a small piece of resistance, and the total resistance is the sum of all the small resistances. And so the small resistances are going to be built out of these disks. So each disk has a resistance, right? If you look at this example, this is a disk, but with its thickness is really, really large, right? And the resistance of this disk was rho times the really large thickness divided by the cross-sectional area. So in this example, each of these is going to be rho times a little tiny thickness divided by an area, right? Where the integral is moving over the length of our resistor. So the area is pi r squared, right? So it's going to be an integral. Resistivity is rho. The area is pi r squared. And then I've got this dl. And I've got to figure out what are the bounds, right? And also, r, right? Doesn't the radius r sort of depend on where we're at in the integral, right? Are we here with this radius, or are we here with this bigger radius? So r down here is actually a function of this thing called L. And L, we might imagine, goes from a starting point, we could say 0, and goes all the way to the finishing point. We'll call it L, all right? Starts at 0, goes out to L. And as we go along there, we're going to increase the radius. So this radius, if you imagine drawing it, you can draw a function of L. This will be the radius as a function of L. This is L equals to 0. And this is when we get to the value of L. And the radius does this kind of a thing, where it starts at R1 and it finishes at R2 with a slope of R2 minus R1, right? So that's the rise over the run. So the slope looks like this. What you can, you can take this and finish the problem, right? So I didn't give you 100% of the details. But the truth is this is a lot of the detail. There's still problems to solve in order to finish this. Books tend to treat this kind of a problem as an example, so you can go and see what happens in their particular example. Books also contain homework problems with this kind of a problem as an example. So I think I've given you quite a lot of good detail for being able to solve these kinds of problems. This right here, this step, you might keep this in mind. This is an infinite number of very short resistors in series. And there is a rule that you would have learned in your laboratory already. Resistors in series add. And that's what we have here. This is a series of resistances. And in order to get the total resistance, we're just going to sum them up, right? Integration is a summation. And in particular, we're thinking of an infinite number of resistances in series where each resistance is infinitesimal. So we can just integrate it. So that's the process that I just showed you. Another quick comment is you'll notice in our result higher up, R, so the resistance is proportional to the resistivity, right? The more resistivity our material has, the more resistance a resistor will have that's made out of that material, right? The resistance is also proportional to the length of the resistor, S. So this is just a series statement. S speaks to how many resistor wafers or really short resistor discs do we have in series, right? That's why it's proportional to S. And R is proportional to the area A. Actually A to the minus 1. So let me get rid of that. It's 1 over A. And if you remember how resistors add in your laboratory when you put them in parallel, they add in an inverse sense, which is so area means the current can flow through this piece or through here or through here or through there. These are all parallel ways of current to flow, and that's why it's inversely related to the area.